Part 2, the natural logarithmic function and integration. Now, if the derivative with respect to x of ln x, absolute value of x, is 1 over x, and the derivative with respect to x of ln of absolute u is u prime over u, then it follows that the integral of 1 over x dx is natural log of absolute value of x plus c, and the integral of 1 over u du is the natural log of absolute value of u plus c. Also, the integral of u prime over u with respect to x integrates to the natural log of absolute value of u plus c. So the work involved in many integration problems becomes a question of whether or not you can get the integrand in the form of u prime over u. So that's really where our work is today. Also, the integral of u prime over u with respect to x is natural log of absolute value of u plus c. So the work involved in many integration problems becomes a question of whether or not you can get the integrand in the form of u prime over u. So if we look at this one here, we can see we're going to evaluate 4 over x dx. I can bring that 4 out in front of the integral so that I'm looking at 1 over x dx. And we can see that that is 4 times the natural log of the absolute value of x plus c. Now, let's not forget our log properties. That 4 coefficient becomes an exponent on the x, and I no longer need the bars because whatever x is, when I raise it to the 4th power, will not be negative. Now, if we look at this example, the integral of 1 over 6x plus 1 dx, you notice that we do not have u prime over u form. If this is our u, our du would be 6 dx. So we are going to multiply and divide by 6. Now our integrand is in the form of u prime over u, so we are going to rewrite it. I just like to do this to make sure I like what I'm looking at. And I get 1/6 natural log of absolute value of u plus c. We're going to substitute back what our u is, and also what is 1/6 is a coefficient. It is 1/6 as an exponent, so the 6th root, again, I don't need the bars because once I'm talking about the 6th root, we know this quantity cannot be negative. It's not necessary to move the exponent up, but you should know how to do it. Sometimes it's advantageous in a problem. All right, evaluate the integral from 1 to 3 of dx over 5 minus x. Well, once again, we know that our u is 5 minus x. Our u prime or our du would be, so u prime is -1, so I need to multiply by a -1. And I'm going to go ahead, since I'm changing things in terms of u, I'm going to change those limits. So g of 1 is 5 minus 1, which is 4. G of 3 is 5 minus 3, which is 2. Now you see we have a problem that has occurred here. First off, I need a -1 inside because I need a -1 dx. So I'm going to multiply by negative both inside and out to get that. And I'm now at the step where I substitute my u is also the place where I substitute my limits of integration. And as you can see here, we have the larger limit of integration on the bottom, and we need it to go from small to big. So we're going to switch the order, and we have to negate it to do that. Well, I already have a negative there, so when I negate the negative, I no longer have a negative. Isn't that nice? And we have u prime over u, which becomes the natural log of absolute value of u from 2 to 4, which is ln 4 minus ln 2. Let's remember, ln a minus ln b is ln a over b. So this is going to give us natural log of 4 over 2, which is natural log of 2, which turns out to be 0.693. Let me remind you, you need to know your log properties. And one other thing, let us remember, ln 4 minus ln 2 is not this. That is a kill me now on the test, okay? Example 4. Find the area of the region bounded by the graph of y equals x squared over x cubed plus 2, the x-axis, and the line x equals 4. Now we're going to look at that graph on the calculator. This is what it looks like. Okay, and we can see we're going to have this integral. Now, if you notice, this is x to the 2nd, this is x to the 3rd. If our u is x to the 3rd plus 2, our u prime is 3x squared. So our du is 3x squared dx. I have the x squared piece, so all I need to do is multiply and divide by 3. And in this problem, I'm going to go ahead and be a little lazy. I'm getting it in the form of u prime over u. Okay, I'm going to get it in the form of u prime over u. So this is 1/3 natural log of absolute value of x cubed plus 2 from 0 to 4. And I can substitute my 4 in and substitute my 2 in. We get 1/3 natural log of 66 over 2, which is natural log of 33. 1/3 makes that to the 1/3 power, gives us this. And on the graphing calculator, that gives us this value. So that would be the integral from 0 to 4. And in this case, since the curve is above the x-axis the whole time, it is the integral is also our area. See example 4 on page 33 for problems on recognizing the u prime over u form in the integrand, and I leave that to you. In order to simplify an integrand to investigate its form, it might occasionally be necessary to use long division. So you should see example 5 on page 344. Again, I leave that to you. Remember, the divisor is missing an x term, so a 0 must be used to hold the space for this term when you divide. Look at that, ponder it. But there's another way to look at that same example that doesn't use long division. Notice what I have here is the integral of x squared plus x plus 1 over x squared plus 1. What if I just regrouped the numerator? I brought the 1 down here and then wrote my integrand as two separate fractions. The integral of x squared plus 1 over x squared plus 1 dx, okay, that's going to be easy, plus the integral of x over x squared plus 1. This is easy. That is 1. This is almost u prime over u. It would be u prime over u if I had a multiple of 2 inside. So I'm going to multiply and divide by 2 to get u prime over u. We know how this integrates now. That's going to give me x. We know how this integrates. 1/2 times the natural log of x squared plus 1. I don't need bars here. Why? Because we're squaring x and adding 1. Already not going to be negative. Okay? And then the 1/2 certainly means square root, and of course, don't forget the C of frustration. Again, see example 6 on page 344 for an example of having to do a factor by factor type of u substitution. Sometimes you might have to add a creative form of 0 to the integrand in order to integrate. So let's look at this. If I multiply this, I get x squared minus 2x. Gee, if this were the perfect squared trinomial, x squared minus 2x plus 1, we could factor it to x minus 1 squared, which would really help with that denominator. So we are going to add a convenient form of 0 so that we get that. So here's my perfect squared trinomial. I have added 1 to get it, because this is actually what I had, but I'm going to subtract 1 right off of that. Okay, so I added a clever form of 0. What that does is it lets me factor this perfect square trinomial to x minus 1 quantity squared minus 1, all over x minus 1 cubed. So I'm going to get x minus 1 quantity squared over x minus 1 cubed, the integral of that, dx, minus 1 over x minus 1 quantity cubed, the integral of that with respect to x. Okay, this is easy because we can cancel x minus 1 quantity squared and leave x minus 1 on the bottom. That's going to be easy to integrate. This is, our u is x minus 1, so our du is 1 dx. So this is going to become u to the negative 3. This is a natural log integration. So this becomes natural log of the absolute value of x minus 1 minus this is u to the negative 3 du. Can't do anything with the natural log. We'll leave it there. U to the negative third integrates to u to the negative 2 over negative 2. So we have this. Got some aloha going on here. Minus minus gives me a plus. The 2 stays on the bottom. And now my u, which is a negative 2 exponent, comes to the bottom. And my u was, for this part of the problem, x minus 1. So here's our final answer. The natural log of the absolute value of x minus 1 plus 1 over 2 times x minus 1 squared plus my C of frustration. Okay, again, see page 335 for guidelines for integration. You'll find that list very helpful. Again, I leave that to you. The integral of 4 over x natural log of x dx could be thought of as 4 over x over the natural log of x dx. Now, if I bring the 4 out, I have 4 times the integral of 1 over x over the natural log of x dx. If my u is natural log of x, my du is 1 over x dx, which I have. So I have u prime over u form. And since I have u prime over u form, that's going to integrate to natural log of absolute value of u. So here's my 4. The natural log of the absolute value of, there's my u, oh, that's crazy, plus c. And then this 4 becomes the exponent on this. Really cool. Example 7. Now, I'm trying to see if there's any connection between secant squared and 1 plus tangent, and there is. If my u is 1 plus tangent, my du is secant squared x dx. I have exactly u prime over u, which will integrate to ln of the absolute value of u plus c. So a natural log of absolute value of 1 plus tangent x plus c. This one, let's see. Negative sign is the derivative of cosine. So I need to add a negative. So I need to add a negative sign, S-I-G-N, to make negative sign. Yeah. Okay. So my u is cosine of x minus 1. My du is negative sine x dx. I now have that. So I have the natural log of the absolute value of cosine x minus 1 plus c. What does that negative coefficient do? It becomes the exponent. What does the exponent do? It does this. Now we're going to do a definite integral. Again, our u is natural log of x. Our du is 1 over x dx. I have that. So you need to start recognizing that when you see 1 over x ln x, you actually have the 1 over x over ln x situation that we talked about in example 6. So there's my u. I'm going to go ahead and change my limits of integration. So g of e is natural log of e, which is 1. G of e squared is natural log of e squared, which is 2 times the natural log of e. Natural log of e is 1, so that's 2. So my e is going to become a 1. My e squared is going to become a 2. So we have from e to e squared 1 over x, natural log of x dx, which is changing my limits when I do my u substitution, 1 to 2, u prime over u, which integrates to ln u. And we're going to evaluate from 1 to 2. Now, let me remind you, when you have used u substitution, do not then go back in and substitute what u was. You've just doubled your work. Evaluate it from this point. Okay, ln 2 minus ln 1. ln 1 is 0, so we have natural log of 2. We want to see example 1 on page 336 for multiplying by a creative form of 1 in the integrand in order to integrate. And you need to know the following. Check to see if I made this correction here. This should say the integral of sine of u to u is negative cosine u plus c. You should know that. The integral of cosine u to u is sine of u plus c. So those should be easy. Now we get into some weird ones. The integral of tangent u to u is the negative of natural log of cosine u plus c. The integral of secant u is the natural log of secant u plus tangent u plus c. The integral of cotangent u is the natural log of sine u plus c. All of these have absolute values. I'm sorry, I'm being sloppy. And the integral of cosecant u to u is negative natural log of absolute value, cosecant u plus cotangent u plus c. Now, that's this book. Other books might say, let's look at this and call that cosine u to the negative 1, which is 1 over cosine u, which is natural log of secant u. That is perfectly okay. Another textbook might do that. If I think about that negative sign right there, that means natural log of cosecant u minus cotangent u to the negative 1, which means this. And if I multiply by a clever form of 1, this gives you, in the denominator, cosecant squared u minus cotangent squared u, which is 1, which leaves you the natural log of the absolute value of cosecant u minus cotangent u plus c. Wow, something to ponder. Your TPs for this video, numbers 3, 7, and 9. See ya next time.